Peaches are transported from 3 orchard regions to 2 canneries. Intermediate stops at a consolidation station are possible. So you have the orchard and station and cannery. Shipment costs are given here. If the no cost is given, shipments are not possible. Draw a network model for this problem. Alright, so let's try to use some letters. R for Riverside, SS for Sunnyside, and Old Farm, OF. Now these are origination nodes because these are the places where the supplies are given. These are supplies. So we start from here. And then there are the stations, the Waterford and Northside. And then the canneries are the final destination, Sanderson and Millerville. And they have capacity of 2,000. The original supply is 1,200, 1,000, and 2,000. Okay. Let's scan this table to draw any arrows. Riverside to Sunnyside. Okay, so you can send between origin nodes. That's something new, but just draw an arrow and put the 1 there. Riverside to Waterford. So Riverside to Waterford, 5. Riverside to Sanderson. Okay, so you can set all the way there, and that's 3. Okay. Sunnyside to Waterford, 4. Sunnyside to Northside, 5. Old Farm to Waterford, 6. Old Farm to Northside, 3. Waterford to Northside. So you can send it here as 2. Waterford to Sanderson, which is 2. Waterford to Millville, that's 4. Northside to Sanderson is 5. Northside to Millville, 9. And finally, from Sanderson to Millville, that's 2. Okay, we have this very complicated diagram, but we have it. Okay, write the LP model for this problem. Define your variables xi, j. And once again, before writing the LP model, it's easier if we number them. So I'm going to number it 1, 2, 3, 4, 5, 6, 7. Here it's 1, 2, 3, 4, 5, 6, 7. And we name xij as number of peaches sent from I to j. Okay. And although this is somewhat complicated, the structure is the same. First, write the origin nodes as inequalities. The transshipment nodes, W and N, should be in equals to out. And then the S and M, those should be the total equals to the demand. Right? And there's a little bit that you have to think about because of this one here and that too. So if you already know how to do this, just focus on how I handle this one here and then this 2. Right. First, R, you have x1, 6, right? 1 to 6, x1 to 4, 1 to 4, and then x1 to 2. And that cannot be more than the supply, which is 1200. SS, okay, you have going out, you have x2 to 4, SS to W, x2 to 5, right? Those are the only outgoing ones. Less or equal to supply 1000. But what about this? Well, see, you have some extra peaches coming from Riverside, and those would add to our supply, right? So even though Sunnyslope can only make 1000 peaches at most, you could add more because there are extra supplies coming from R. So that's actually the important part. Okay, that's the thing that you have to pay attention to. That's the challenge in writing the LP model for this problem. Okay, Old Farm, x3 to 4, x3 to 5, and those are the only outgoing ones, and it should be less or equal to 2000. Okay, now the transshipment nodes. Since these are the only origin nodes, these are the only inequalities. After this, it's all equalities. Okay, Waterford, we have all the incoming ones, x1 4, x2 4, x3 4, equal to the outgoing ones, which is x4 to 5 is an outgoing one, x4 to 6, x4 to 7. For the north side, it's the incoming ones at x2 5, x3 5. I don't see anything coming from R, right? R to N, there's nothing. R to N, there's nothing, okay? But there's one coming from the Waterford, which is x4 5. These are everything coming into the north side. And then 5 to 6 is the outgoing one, x5 6. x5 to 7 is another outgoing one. Okay, since I don't have any room, let me write it down over here. Or let's write it over here, S. Okay, you have x1 6, x4 6, x5 6. These are the everything that's coming in. Now, what about this going out? Well, usually destination nodes have nothing going out. So let's think about how to handle this. If you have something going out, that means you're losing it, right? You're losing how many, whatever that's sent to this Millville, we're losing it. So we should subtract it. So that's actually the new part. X 6 7 should be subtracted. And that's the tricky part, okay? Yeah. Okay. And other than these two things, the rest of them are pretty straightforward, okay? So that should equal to 2000. Okay. Now for the M, I don't have a space, so let's write it here. You have x 4 7, x 5 7 plus x 6 7. These are everything coming into Millville, and that has to equal to 2000. Okay. Now, in addition, we need the objective function, right? So let's write down the objective function. We just have to write down the coefficient times the product of the path, the number of peaches. Okay, so it's pretty much these variables. So okay, x1 6 times 3, x1 4 times 5, x1 2 times 1. Okay, plus. So we did 3, 5, no, 1, 1, 5, and 3. I guess it's easier to use this. Okay, so it's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, good. So let's go 2, 4. So 4 times x2, 4, plus 5 times x2, 5, plus 3, 4. 6 times x3, 4. 3 times x3, 5, plus 2x4, 5, 2x4, 6, 4x4, 7. I'm reading this line here. Just 2 more lines to go. 5 times x, 5, 6. 9 times x, 5, 7. And finally, 2 times x, 6, 7. So that's your objective function, and you have to minimize. Okay? So that's it. It's really a straightforward problem except these two places. If you just pay attention to these two, you're good.